Let's continue. The second lesson after the core of today, from Zalamea.
Thank you, Professor Gomez. I will begin first recalling what may be the keyword of yesterday lectures, not only mine, but every lecture insisted on that word, which is fundamental for us, diversity. Diversity and plurality were names repeated a lot of times, and particularly also in the presentation of the official trailer for Unicamp. Diversity. Diversity, fundamental for our understanding of the world. The plurality is a key for approaching the richness and the complexity of whatever is around us. So that kind of diversity and plurality was expressed in a more mathematical way using the name of variety. We want to understand the varieties of the world. And particularly in mathematics, we want to understand the main varieties of the mathematical understanding of the world, which are algebraic varieties, topological varieties, differential varieties, combinatorial varieties, etc. And in particular, inside of all of them, logical varieties. Logical varieties are just a small part of the mathematical world. That big mathematics world is very interesting for the philosophy. The philosophy of logic, of course, is also very interesting, but it's just a part, small part of the understanding of the philosophy of mathematics. In that way, we wanted to express the idea that the logic is a part of mathematics and not the foundations of mathematics, but a part of mathematics. And we have the mathematical tools to try to understand those different logical varieties. That one was one of the main approaches. The second main approach was the hypothesis that the essential thought, mathematical thought, is a human construction. It's a creation of the human mind, of the human civilization, and in that perspective, mathematics is extremely dynamic. It's something which moves completely in the development of history, and which has several moments in its development. In many of the courses that we have seen today and yesterday, we see that the reason has to change and has to adapt in terms of Batten's logic, the adaptive logic, or it has to introduce some richness in the sense of the consistency or some other deviant perspectives which are fundamental for those. So this richness of the mathematical world is reflected in part by the richness of the logics. That's something important, and that richness is an evolutive richness. We evolve, mathematical thinking evolves on the development of history. And in those developments, you have several important polarities. For example, space and number, finite and infinite, heart and reason. There is one which is very important, which is beauty against truth. Today, for example, in one moment, Marcus, which is a very hard-working logician, said that the real reason to do this is because I love it. Love. There is love. There is some kind of love, some beauty, which is fundamental, beyond even truth. We will see in a moment a wonderful definition by Russell, which was not well understood, but if we try to capture the important idea of Russell, we will see that beauty is something very fundamental for mathematics, even beyond truth. So today I will be speaking on the analytical perspective. The analytical perspective on classical logic and set theory, and particularly the Anglo-Saxon school. Yesterday we were presenting those different polarities, and then we asked as something fundamental, what are the different mediations between the polarities? And those mediations in general make some of the important and big constructions of mathematics. Again, insisting on the idea of variety of perspectives. Yesterday began with the Riemann-Roch theorem, a central theorem for algebraic geometry, and we may begin today with Lobier's diagonal argument. Lobier passed away, 2 weeks ago, one of the greatest mathematicians of the last 50 years, and certainly the greatest figure in categorical logic. He was the master of many of us. Lobier in the 60s proved something beautiful. A very clever, very simple, extremely simple argument that you can do in a very general perspective, which are called Cartesian closed categories, in which you have a small argument, called the diagonal argument by Lobier, and which explains at the same time the diversity, the variety, the plurality of things which seem completely unrelated. On one hand, Cantor's theorem, between when you take the power of the set, you make a cardinal bigger than the set, Cantor's theorem. On the other hand, the incompleteness theorem by Gödel. On the other hand, the fixed point theorem by Brouwer in topology. And on the other hand, the fixed point theorem of Tarski in complete lattices. These things seem completely apart. Complete lattices, sets, proof theory, etc. Things which are completely different. You have a variety of differences. You have very different types, but beyond that, there is something. Beyond that, there is a universal construction. Beyond that, the Lobier diagonal argument, which proves in particular cases all of those constructions. If we had, it's not something difficult. If we had 1 hour with these wonderful blackboards, we would be able to prove the Lobier argument in 1 hour, writing all the blackboards we did. So it's something very simple, but with that you prove that there is a strong unity beyond diversity. That is something which is fundamental, I think, for our understanding of the philosophy of mathematics. The philosophy of mathematics has to take care of the plurality, of the diversity, of the trans, which is very important for all young people today. The transits, the transgender, the transitions of the human being, the transition of the human to the machine, etc. There are a lot of transitions which are fundamental for young people today, and which are captured very well by this idea of different types. But beyond the different types, you have some universals which get a construction, a real profound understanding, a unitary understanding of diversity. So diversity on one hand, okay, but then afterwards, the philosophy of mathematics always has tried to go beyond the appearances, beyond what we can see. In a sense, one of the beautiful approaches to mathematics is the mathematician is interested in what we cannot see, what is invisible. That's interesting for the mathematician. It's not what is clear. We will come back to that. We are not interested in what is clear. We are more interested in what is very, very dark. So, let's present quickly our session of today. Analytical philosophy, more related, you will see why, to classical logic and set theory. And I will emphasize the Anglo-Saxon school, thinking in English. with some very important and very interesting names that you will see there. I will present before like the general framework, and then afterwards we will concentrate in some very interesting thinkers in the Anglo-Saxon school. Some of them extremely well known, some of the others completely unknown. We will see about that. And I have to try to put them in what I think is the descending order of interest for mathematics. And then we will try to do a critique of this school, which produces a lot of beautiful things, but also which produces very harmful things at the same time. So talking about the dialectics and the polarities, this is one of the fundamental dialectics of thought. On the one side at the left, you try to understand the concept, making an analysis of the concept, going to the basics of the concepts. You decompose, you make a decomposition of the concept. You get either the elements or the atoms. And in that line, you are doing analysis, an analysis of the construction. There is a big, very important theory on the analytical side, which is set theory. By definition, by the very definition of sets, sets construct the world through elements, looking at the decomposition of the structures. That's the one that we are going to insist today. Tomorrow we will insist on the other part, thinking about this pendulum, in which you have to work at the same time on one side, but also on the other side, in order to get more or less a fair comprehension of the complexity of the world. So I will not insist on the right part now, but I will only say that some of the most important philosophers of mathematics in the history of the philosophy of mathematics were able to work precisely on both of them. Today, Aristotle was very much insisted as the father of logic. Plato is the contrapositive, and Plato is the father of the philosophy of mathematics. And the quarrel between Aristotle and Plato is still a quarrel between logic and the philosophy of mathematics. It's still today the same, but with a lot of more information that has been gathered along the centuries. But the other two great, I think that there are three major philosophers of mathematics in history. One is Plato, the second one is Leibniz. Leibniz also worked very much on both of them, on both constructions. He was one of the founders of the calculus, as you know, so the analytical part was extremely important, but also he was one of the founders of synthetic calculus. And the third one, which was mentioned by Itala yesterday, Peirce. Peirce is the great philosopher of mathematics. The three of them are certainly the greatest philosophers of mathematics in history, even from the Greeks to today. They are still the most original, the most profound thinkers about mathematics. And the three of them were, at the same time, analyticians and syntheticians. But I will insist today on the analytic side. Also, yesterday, after my talk, one of the comments of the students was extremely interesting, in which he said, why are you talking so much about polarities, the dyadic contraposition between something and the other? And he's entirely right. This is only like the first simple approximation to the basics polarities of knowledge. Beyond the dyadic constructions, we should go to at least triadic constructions. We should think in three things at the same time, all the time. If you are systematically triadic, you become a Persian. Peirce was insisting all the time in his life that we think in triads. And the semiotic of Peirce is extremely important today. Why? Because it's a triadic semiotics well beyond the dyadic semiotics of Saussure. So Peirce is the one who is today very important, not Saussure, because Peirce was triadic. Here, I am thinking on the very basic level, just linear level of the dyadic construction. But today, for example, Marcus at the end of his presentation of today was already presenting some kind of change in which he wanted to not only talk about a linear consequence relation, but a two-dimensional consequence relation. And he said, I love it. Why? Because the multidimensionality will bring you a better grasp of the complexity of the world. So this multidimensionality will be fundamental, not only for logic, but for thought in general, and beyond these polarities and this dyadic first approximation, you should think in triadic terms, and I think more than that, you should think in geometrical, multidimensional terms. That will be our goal at the end of this course. Approaching the understanding of mathematics and of logic using geometrical multidimensional tools. So we begin in the analytical tradition with possibly the greatest analytical mind that has existed. Of course, Cantor. Here you have a short map of Cantor's most important contributions. The key for the understanding of Cantor's contributions is again a polarity. The fundamental polarity that he found between a continuous understanding of the continuum and how you can get a grasp of that continuum, which usually is beyond our understanding. So he had this incredible idea that to understand the continuum, you have to go through the best of the discretes, the well-ordered. The polarity between the discrete and the continuous is the key of all the Cantor constructions. And he invented a lot of beautiful technical tools to understand that polarity. He invented, of course, the constructions of the real numbers, at the same time with other mathematicians. He invented indexes for those signs, which at the end will be the transfinite ordinals. He invented the many number classes which made a hierarchy of different infinites. He was able to prove the not equivalence of the basic constructions between the continuum and the discrete, etc., etc. He invented the alephs and the ordinals. In a back and forth also, this is another very important polarity. In a back and forth between interior and exterior. Also today in the course of logic, one of the main things was to internalize in a sense, some logical ideas, to internalize them with connectives. That's something very classical, a very tradition of thinking in logic, in which you can say that many of the most important things in logic are to convert in an explicit way some implicit things. You have implicit relations in the world, you can make them explicit through logic. That's one of the main approaches to logic. And that's something that Cantor did extremely well, and he was able to do that with one of the most beautiful definitions ever done in mathematics. What is a set? The famous definition by Cantor is a set is something which can be made one to the many. A many, which is understood as a one, is a set. With that definition, which was not understood, of course, in the moment and was extremely criticized, and Cantor was said, you are a theologian, not a mathematician, etc., etc., things very strong against him. this beautiful and wonderful definition of set. What is a set? Is exactly what is a many in one. With that, if you do a little work, we could do it also if you want in the questions afterwards. In a little work, which wouldn't take me more than 5 minutes, you get from the definition of Cantor the axioms of Zermelo immediately, doing with care this definition. The many into one produces you the pair axiom, the union axiom, the power axiom, etc., very easily, very quickly. So this definition, which seems theology, is in fact extremely interesting for the foundations of mathematics and the foundations for analytical mathematics in one moment. And Cantor already was perfectly aware of what was the inconsistency. We have talked a lot about inconsistency in these days. It was clear for Cantor already. What is inconsistent? For Cantor, the definition of inconsistent is the many which is not in one. That's an inconsistency. And he proved, of course, something that you will know very well, the set of all sets is a many which is not in one. Or the set of all cardinals is a many which is not in one. Or the set of all ordinals is a many which is not in one. So he had very clear this idea of inconsistent multiplicity, and he did something really amazing in a letter to Hilbert in one moment. He had this brilliant idea that if we allow this to work with these inconsistent multiplicities, then he had more or less the idea that you could prove that any set can be well ordered. That's the axiom of choice. That any set can be well ordered. If you allow inconsistent multiplicities in the world, then with that, descending the inconsistent multiplicity at the level of a set, then you can show that the set must be well ordered. The idea is very simple. If the set is not well ordered, then you will make inside of the set all of the ordinals, and then if you take all of the ordinals, that set will have a large volume, and it will not be a set. It will be a many, which is not in one. But that's a contradiction because we began with the set. But it's a very clever and very profound idea that using the idea of inconsistency, you could try to prove the well order, and for Cantor that was fundamental. Because with the well order, the good order, then you can understand the continuum. So this is, for me, the example of the greatest analytical mind, in the sense that it has this incredible richness of a clear polarity, then a lot of techniques to understand, he invents the techniques to understand that polarity, but then he goes well beyond the polarity, and he allows to go to the inconsistent work and then try to come back. So, in homage to Cantor and Loffredo also, here we have this polarity again, this diagonal argument, which is fundamental. One of the key techniques for Cantor is to make the universe of sets grow. You take the set, you take the power of the set, it is growing. The fundamental theorem of Cantor. But that for Loffredo is just a special case of a general diagonal argument. So set theory with Cantor becomes, in a certain moment, the paradise for mathematics. You know the famous Hilbert word, we will not be thrown away from the paradise of Cantor. In fact, the influence of Cantor is gigantic on Hilbert, is gigantic on the 20th century, is gigantic on the construction of set theory. Set theory in one moment using the actions of the followers of Zermelo and then Frankel, with Zermelo-Frankel, the system of Zermelo-Frankel, it was shown that the idea of the constructions of mathematics can be mimicked, represented in set theory. We will talk about that representation at the end, and we will see what are the profound epistemological and ontological problems which are beyond that reduction. Here in this diagram, you will be able to follow the different paths. In fact, yesterday already I put my slides in my page in academia. It's already there. Someone asked me, I didn't see it. It's because academia organizes the information first by books, then by articles, and at the end you have the preprints. So I put that as a preprint, so it's at the end of the page, but it is there.
Sorry.
Yes?
I want to know in the definition of carbon, why are there two references?
Well,
In the definition of set and carbon, why there are two references?
yes, because simply it's repeated afterwards. The first definition is in 1883 in his famous paper on set theory, but then afterwards it is taken as a truly first definition in the 1895 paper on the contributions to transfinite numbers. So it appears two times in Colombia. Thanks. But you can see also in the dates here how imaginative was Kant. As I would say all of the great mathematicians are extremely imaginative in the sense that they are often able to understand something and the contrary at the same time. We will see that particularly with Gödel afterwards. In our sessions, in our fourth session, in which Gödel will appear in an important way. Gödel is one of these geniuses in which he was perfectly able to prove at the same time completeness for first-order classical logic and incompleteness for the plano arithmetic. At the same time, he was proving the two things at the same time. His famous PhD thesis proves the completeness in the famous article of Gödel, 20 pages. PhD thesis doesn't have to be gigantic if it's extremely good. So when we think about set theory, then afterwards with the formalizations and the axiomatization that come after Cantor, we are thinking about Zermelo-Frankel, and in Zermelo-Frankel you have these wonderful properties about the underlying logic of Zermelo-Frankel, which is the classical logic. And in classical logic, the sets behave extremely well in the sense that you have the compactness theorem. If you have a theory, to have a model of that theory, you have only to have different models for the finite parts of the theory, the compactness theorem, and then the Lowenham-Skolem theorem, in which you have, to simplify things in an enumerable language, if you have a model, an infinite model, then infinite model can go back and forth along the scale of all the values. Lowenham-Skolem and compactness are two properties of set theory which are well captured by classical logic. This is explained here. First order classical logic shows by Lindström's theorem in the 1960s the central place of this logic, with respect to set theoretical requirements, the Lógica column and the compactness theorem. If you want precisely a logic which verifies the Lógica column and compactness and which extends the classical logic, it has to be the classical logic. There is no other logic behind that. If there is other logic, it will fail either compactness, either Lógica column. So classical logic becomes a very central and for very technical reasons, for very profound reasons, becomes the natural logic to do sets. If you are interested in the analytical perspective of going inside the set and looking carefully at its element and construct carefully the idea of the structure through its decomposition, then classical logic, first order classical logic, will be the nice and natural logic to do so. If you are not interested in the analytical perspective, then you should change your logic. And that's something that we will talk about afterwards. And in fact, as we have seen in other previous courses, parallel courses to this one, the variety of logics is fantastic. We are interested in the variety of logics in which we have a lot of different possibilities. You have the basic logics, then you have many valued logics, then you have intuitionistic logics, the paraconsistent logic, the modal logic, etc., etc. It's a very big fabric, and that in that very big fabric, classical logic does not have a particularly important place unless you are interested in sets. If you are interested in sets, then you should do first order classical logic because it's the natural logic related to sets, to the most important properties of the model theory of sets. Something which is clearly explained by Lindström's theorem. So let's go a little back to see where this begins. Beyond the great mind of Cantor, that's a mathematical, analytical, and logical mind at the same time, and also driven by things which are well beyond mathematics. You know that Cantor was particularly interested in approaching a sense of God, something which is beyond our understanding of the infinite. So that's the name for the transfinite. Transfinite goes as steps, little steps, to approach something which is beyond the transfinite, which is the absolute, which is a sense of God, and that sense of God is here in the inconsistent multiplicity. For Cantor, an inconsistent multiplicity was a way of reflecting the richness of God. We are not talking about that in this moment, but we will be coming back to this kind of strange things that mathematicians do in some moment, in which mathematics is very much related to profound human questions, not just technical questions. That's very important for the mathematician to try to go to the deep questions of the understanding of the world and the understanding of the mind. Technique is just a part, the very important part, extremely important part, but should not characterize mathematical activity. And I will try to show at the end of our course that we can, at the same time, be careful and take care of the extremely important part of the technique, but at the same time, to be open to things which go well beyond the technique, which are the profound ideas beyond the techniques. That can be done in a very precise way. We will be seeing that at the end of our course. So let's begin with the master of this kind of thought at the beginning, which is Bertrand Russell in this work, the Principles of Mathematics of 1903. Russell at that time was a very young person. Many of the writers and thinkers that we will be talking about today and tomorrow were very young when they were changing our understanding of the philosophy of mathematics and our understanding of mathematics in general. He had just 30 years, like many of you here. So the Principles of Mathematics, not to be confused with the other very important work by Russell, in collaboration with his professor, his master, which was Whitehead. Russell and Whitehead wrote a very important and very fundamental work, which is called the Principia Mathematica. It's a gigantic volume, gigantic volume of 3 cents, extremely technical, in which they tried to reduce, in part, mathematics to logic. We know that the reduction didn't work, because in the middle of the reduction, Russell had to introduce types, and then to make types work in the mathematical, practical work, he had to introduce an axiom which is called the reducibility axiom, to come from very high types to lower types. And that reducibility axiom is a kind of infinite axiom. So beyond the desire to reduce mathematics to logic, there was a kind of hidden infinity which was introduced in the axioms to the reducibility axiom. That was a very important axiom for Gödel, if we will be able to talk about that afterwards, if I recall to do that afterwards. One of the main problems introduced by Cantor was to understand what was the size of the continuum. The famous continuum hypothesis says that the size of the continuum is exactly the next size after the natural numbers. The size of the real numbers is exactly the next size, infinite size, beyond the natural numbers. That's a very important problem, which was left open by Cantor, and Gödel was the first to introduce what are called the consistency models for the continuum hypothesis, in which he showed in a restricted model that the continuum hypothesis is true. The constructible universe by Gödel is a short universe in which things do not explode, and in that small universe, the continuum hypothesis is true. The idea to construct the universe of Gödel is to make a small change on the axiom of reducibility. So these things are extremely interesting in the history of logic. But here we are at the beginning, when Russell is just a young man at 30 years of age. He has already found that contradiction that was talked about in the previous course with Buttons, with the Russell contradictions. And he began to write a text on how to understand mathematics in general. He had already done his PhD on the foundations of geometry. So he was a very special, very wide mind. The Principles of Mathematics is a gigantic book also. Here we can see how many. These are the quantity of chapters or sections on the book. You have like 500 sections, and each section makes 1-2 pages. It's a gigantic book of 1,000 pages. Completely amazing book. I will say, probably without any doubt, that is the most important book ever written on the philosophy of mathematics. It's pretty clear that nothing is short to accomplish what Russell did. It's extremely profound, it's extremely wide, the diversity is incredible. We will see that in a moment. Just looking at the index of the book, extremely profound, open to all diverse possibilities, a really strong effort by a young man to understand the world of mathematics. We can see it here quickly on the table of contents. So he begins here with definitions of pure mathematics, and then he passes to symbolic logic. Here we will appear the famous definition by Russell, which is one of the beautiful definitions of mathematics, which was mocked often by many people, which was certainly not understood, in which Russell said more or less that mathematics is the science in which we don't know what we are talking about, and we don't know if what we are saying is true. That's a famous definition by Russell, which seems a calembour, a joke, but it's not a joke, it's an extremely good definition. Mathematics is the thing, is the science in which we don't know what we are talking about. That beginning is extremely important for the mathematician. The mathematician is explicitly interested in what he or she doesn't know. That's which drives his or her research. Okay, that's something very important. We don't know. We don't know that invisibility is fundamental for mathematics. If everything was clear, mathematics wouldn't exist. So beyond clearness, and I will go here to the first alternative, the analytical tradition wants things to be clear, crystal clear, no doubt. Everything should be clear. That's not mathematics. Mathematics is extremely dark, with a lot of very blind points. And the blind points are the things which are important for the mathematician, not the things which are clear, not the deductions. What is important is the idea which propels the deduction. And that idea is often extremely dark, extremely contaminated. We will come back to that. That's very important for the mathematician. And that is well taken care in Russell's definition. Mathematics is the science in which we don't know nothing about, and we don't know if what we are talking about is true. So mathematics is not related to truth. Truth is something more specific of the logician. The logician is very interested in truth, in the variety of truths, the differences of truths. That's extremely important. But the mathematician is more interested in the harmony, in the beauty, which propels the truth afterward. If the mathematician were the inventor of mathematics, say, the ones which are really important for us today still, Galois, Riemann, Poincaré. We will come back to that afterwards at the end, if I recall. Galois, Riemann, and Poincaré, extremely important mathematicians, producing profound ideas, which are extremely important for the beauty and the harmony of mathematics, in which logic doesn't appear at all. Logic wasn't invented, mathematical logic, at the time of them. So mathematics goes perfectly well without the logical structure. And it was also taught today in one of the questions, if there is an inconsistency in Cervelo-Frenkel, will the mathematicians care? No, they will not care at all, because mathematics is well oiled. It's functioning extremely well, completely independently of the foundations. Those are two things completely different. Mathematics is not interested in foundations. Mathematics is interested in understanding the deep relations between the different varieties of the mathematical thought. Very different. But that is captured extremely well by Russell, with that strange definition, which we can think he was, what was he thinking? He was thinking exactly in the right way. Mathematics is the science in which we don't know what we are talking about, because what is interesting in mathematics is not our actuality, but the possibilities that mathematics will construct in the future. The realm of possibilities is fundamental. Yes, the question?
So you said that mathematics extremely dark.
I can understand.
You are saying that mathematics is extremely dark against what? What is the paradigm of clarity?
Okay, that's the contraposition that I want to make. What should be clear in principle would be nice actions, nice deductions, and clarity, clearness in the deductions. That makes you a sense of clearness. Something is clear. But beyond that, in that sense, you have like representations of ideas, and those representations of ideas are put in an order, and that order gives you some clearness. But that's not the way that the mathematician invents. The mathematician invents not doing deductions, not doing definitions, but having strange images, strange contrapositions, harmonic view of different structures, and then that drives the definitions, then that drives the deduction. What I more or less I am saying, but that will be clear in our last session, is that beyond the clear apparatus of actions, definitions, and deductions, there is another part which is extremely important also, which is the imaginary mathematics, the metaphoric mathematics, the images which are a little vague, but which are fundamental. Both of the things, again, in my pendulum perspective, are fundamental. You cannot say mathematics is just deduction, but you cannot say either mathematics is just abduction, in persistence, the invention of hypotheses. Yeah.
Just follow up. For instance, in the work of art.
Please speak it, stand up and speak.
For instance, in the work of art, if any work of art that anyone can think of, they love. There is no goal of understanding that thing in its totality, or here thinking about that. But in mathematics, the aim is clarity. It is that what I am saying, what I am trying to communicate in mathematics, maybe it is dark at first, but the goal is clarity that you will achieve by understanding.
Perhaps yes. The idea is to share that intuition that we got with the image, with the profound harmonic construction of the world. And one of the ways to produce that for the community is to introduce a language in which we can converse and dialogue in a controlled way and in a structured way. But both of the things are important. And your example of art is extremely interesting. And I will explicitly come back to that at the end of my course, in which I will try to show you the construction of something that I am calling mathematical criticism. There is an art criticism, there is a literary criticism, there is a film criticism, there is no mathematical criticism. It's strange, because it should be. Mathematics is a creation of the human mind, one of the beautiful, great creations of the mind, and there is no mathematical criticism to understand that. We will talk about that afterwards. So let's come back to Russell. Beyond this fantastic definition of pure mathematics of Russell, he begins, you can see, I will go very quickly on that, symbolic logic, the implications, the denotations, the classes, propositional functions, relations, a whole chapter on contradiction, and then he passes to the idea of number in a profound way with what he has learned from Cantor. So not just understanding the natural numbers, but really understanding the different numbers which extend the natural numbers. So he talks about cardinal numbers, he talks about words, fractions, introduces the ordinal numbers, quantities, he talks about zero, he talks about infinitesimals, not just infinity. So you can see here the wide variety, the diversity, again, the plurality of a good mind. A good philosophical mind should be plural and diverse. This very young British logician and mathematician is the example of diversity. And you know that also afterwards, when he will be outside mathematics, he will be also an example of plurality and diversity in his life, in his very life. So you have here the order, the idea of order. He's seeing well before Bourbaki, well before the basic fundamental structures for Bourbaki are topology, order, and algebra. That's very clear for Russell in this moment, well before the construction of mathematical structures by the Hilbert School and by Bourbaki. He talks about the ordinal numbers, then about infinity and continuity, the construction of the real numbers, the transfinite ordinals. He continues and continues. The philosophy of the continuum, of the infinite, multi-dimensions and complex numbers. It is there. Probably, I think, I may be wrong, but probably the most beautiful invention of the human mathematical mind are the complex numbers. Because the influence and the profound drive of the complex numbers has explained things which are completely impossible to understand without them. Beginning by this very world in which we are living today. You know that we depend on electricity, and Maxwell's theory of electromagnetics was invented using quaternions, not just complex numbers, but quaternions. He needed quaternions to produce his laws on physics. So physics, the complex numbers are very well inserted in our world in things that in ways that we cannot really understand very well. Roger Penrose, the great physicist, says also a lot of times that the complex numbers are the key to understanding our world. That was important for Russell also, for this young philosopher of mathematics, and the geometries. So he was interested in the multidimensionalities that we were talking about a moment ago, not just the dyadic world, but multidimensional worlds, in which the first and important one are the complex numbers. The complex numbers are like the heart, the real heart, of the most important mathematical constructions from the modern times to today. They are everywhere. And they are beyond, of course, the Riemann-Roch theorem that we talked about yesterday, but they are also beyond the Wiles theorem that Carnielli was talking about yesterday. The proof of the Fermat theorem needs a lot of complex numbers, and it is beyond the constructions of this young particular genius, which is Galois. They are everywhere. But this philosopher, this young philosopher of mathematics says, okay, we have to look at the complex numbers. Don't forget, because he is the master. And we will see what happens at the end of the century following the master. It will be really awful. Terrible. But here, the master, the young master, is really open to everything. He's open to algebra, he's open to space, he's open to logic, he's open to physics. All of this in this incredible, really incredible text that should be read, I think, by all of you in some moment of your life. It's something that changes you completely. When I read for the first time Russell, I said, wow, he's very, very far away of everything that we know. It was fantastic. The Principles of Mathematics by the young Bertrand Russell, not to confuse with the Principia Mathematica by the late Russell and his master wife. In fact, that's a book that has almost never been read, the other one, the Principia Mathematica, except by the famous girl.
One good reader. That's what I want.
Yeah, one good reader. That's the idea. Well, this is like the ideal. After setting the ideal, what can be done? A century afterwards, what has been done in very lesser things. But one of the interesting things which are not at the level of Russell of the Principles of Mathematics, but which is extremely little known, is this small treatise called Lectures on the Philosophy of Mathematics by one completely unknown American mathematician called James Byrne Shaw. Have you ever heard Shaw? I would say no. No one has ever heard about Shaw. Almost sure. It's very, very little known, extremely little known. And he has a treatise written in 1918 called Lectures on the Philosophy of Mathematics. He was a mathematician from Ohio, and a statistician from Ohio, but he was an extremely open mind. You can see here the contents of the book. The contents of the book still today are completely amazing. The meaning of the philosophy of mathematics, number and arithmetics, space and geometry, arrangements, the logistic and the reductions of mathematics to logic, operators and the reduction of mathematics to algorithms, hypernumbers and the reduction of mathematics to algebra, processes and the reduction of mathematics to transmutations, etc., etc. And then he shows that all of these reductions have failed. All of these reductions have failed, and that there are other important principles that mathematics should take care about. Some of them are forms, invariants, functions, and in general, the variety of mathematics. Here at the end of the book, you have a wonderful, wonderful table. It should be like also an ideal table of what a philosopher of mathematics should do. He tries to understand the complexity of the world of mathematics using structure and central principles of mathematics. So he's talking about in 1918, well before the Hilbert School and well before Unicamp. But he's already pointing to what will happen at the middle of the century. You can see there all the basic constructions of mathematics. In here, you can see the idea of a dynamic mathematics related to transitions, and then a static mathematics related to ranges, in which you can, with care, see what are the different constructions of the mathematics of that time. For example, to just take whatever special part of the table, the importance of the automorphic functions, functional equations, functional analysis, even just after the invention of functional analysis by Hilbert, and little time afterwards the invention of automatic functions by Poincaré. He was extremely aware of what was happening at that time, and he was trying to produce a general classification and understanding of mathematics using very simple and key ideas. The idea of invariance, for example, which is fundamental for us, fundamental for mathematics. I was beginning today my session with the idea of diversity and variation. We're interested in diversities and variations, but beyond diversity and variation, what is important is the invariance. What is important beyond the different types are the fixed points, the invariance. What is important beyond the different types are the universals. That was pretty clear for Shaw, and he insisted also on something which is important for the development of modern and contemporary mathematics, the idea of function. Beyond functions should be relations, but functions already are very important for the development of modern mathematics. If you go beyond functions, which are more dyadic, you can introduce relations, and then you open up new perspectives, the multidimensionality that was not done by Shaw, of course, but he pointed out to these three important constructions: invariance or universals, functionalities, and idealities. Importance of construction of ideal images for mathematics. The mathematician is interested in that thing that he cannot see, that he cannot talk about. That's an idea. This table, I will not have time to go through it, but you should try to find out the book. It's extremely difficult to find out because it's not in PDF in the Google world, I think, but there are just a few copies scattered in some libraries. But I have written a lot about Shaw, so you can find it in my books. I will talk about the books afterwards at the end. Another young genius, 30 years also of age, Wittgenstein. The first Wittgenstein, the famous Tractatus Logico-Philosophicus, the basis of analytical philosophy, in which the young Wittgenstein tried to be extremely clear, tried to reduce the world to facts, to atoms, and then to introduce propositional properties about facts and atoms, and with that he tried to produce a nice and reasonable image of the world. That was an impressive effort also, in which language, syntax, and the idea of going to truth values and propositions and atoms was extremely important in the line of looking for the composition, the final decomposition, atoms here, atoms of the language, instead of elements of the sense. But this is the same idea, the idea of decomposing the object to its bare minimum, and with that try to reconstruct the world. That was an impressive essay. At the end of the essay, Wittgenstein says we should talk about propositions, facts, and if we cannot about that, we should remain silent. I think that's very important for Wittgenstein, very important for philosophy in general, but very bad for mathematics. Extremely bad for mathematics, because we should not remain silent when we are beyond propositions, values, or atoms. The mathematician should talk loudly, not remain silent, about the things that explicitly in the first Wittgenstein are out of the question. Aesthetics, that's out of the question. We We cannot talk about aesthetics. It's not something that we can understand with facts, atoms, propositions. We cannot talk about metaphysics. Metaphysics is banned and should be banned of the human mind. That's something very strong, very, very good for a young people, for a young person, extremely important for Wittgenstein, extremely important for the history of philosophy, but extremely bad for mathematics. Because mathematics needs aesthetics, needs metaphysics. I will come to that strongly in the following sections. Mathematics needs beauty, and mathematics needs the idea of a relative universal. If we cannot talk anymore about absolute universals, we should and can talk about relative universals, which are something beyond the usual appearances, beyond types, and which introduce the idea of an archetype fundamental for mathematics. Very, very important for mathematics. So beyond this first Wittgenstein, which is extremely brilliant, of course, fantastic aphorisms in which language and form and syntax take all the way. But then Wittgenstein also, as I mentioned, as all great minds, is not a dogmatic person. If you find a discussion with a dogmatic person, you should escape quickly of that dogma. That's not the intelligence. The intelligence is at least to open up the mind, the plurality. Then afterwards, then you have to integrate the plurality. Wittgenstein is a good example of that. You have the second Wittgenstein, which goes completely against the first Wittgenstein, completely against, in which he says that was something, a dead end. We couldn't continue in that line. And he introduces beautiful and also wonderful perspectives, more dialectical, more pragmatic, about action, about gains, and trying to bridge all of them, the first Wittgenstein, the second Wittgenstein, you find a natural and very, very sound finitistic constructivism, which is finally the basic position of Wittgenstein. So here you have a strong tradition at the left in which language and syntax and propositionals and truth values and anatomistic side of the world is clearly stated, but on the other side you have more the idea of we are not so interested in those atoms, but in the actions between the atoms, in the more holistic perspective, integral perspective, in which the construction of the human mind takes a more strong form. So the pendulum in Wittgenstein is also clear. This is a way of making again the statement that we need plurality. We need the plurality. Another figure. So Wittgenstein is extremely important. Here we have a hierarchy. I would say this is the maximum construction of what we may take as the basic trend of analytical philosophy of mathematics, with the principles of mathematics of Russell. Then we have this fantastic and extremely little known American mathematician, James Bernichow, which produces like a real understanding of the complexities of the mathematical world in 1918. Then we have Wittgenstein, which will have a gigantic influence on philosophy, and I would say zero influence in mathematics, without any doubt. A lot of influence on philosophy, a lot of influence on logic. Mathematics, nothing. Mathematicians don't know nothing about Wittgenstein, and Wittgenstein never said anything important about mathematics, even if he wrote a lot of things about mathematics. mathematics is much to say. He talked about a lot about induction, about logic, but about mathematics in general, not. And we will finish in a moment with some considerations about that. A very important person also in this tradition, Quine, also a very young man when he writes his New Foundations for Mathematical Logic, in which he produces new models for set theory, in which you try to refute some of the fundamental constructions of the Cantorian set theory, the action of choice and the well-foundedness, and he produces beautiful models for a new set theory. He has 30 years of age in the moment, and that's one of the famous constructions of Quine, and the other one is the famous two dogmas of empiricism, which goes also in the pendulum construction. You can see very different from the first Quine. 14 years in the middle, and in fact in the middle, as I was learning from a paper from Ottaviano and Gomez, Quine visited Brazil in 1934, I think, 1934 or 1932, then 1934, I think. He visited Brazil in 1934, and it was a very important presence for the beginning of the Brazilian school in logic. In the middle of the two, then you have the logician, which is trying to produce new foundations for logic, but then the philosopher of logic, in which he discovers that there is no good single distinction between analytic and the synthetic, that you have to think holistically. You cannot take different statements and then that specific statement is analytic or synthetic. You have to think holistically, and then the distinction is blurred. That's something very interesting for us also, and for the consistent perspective. The blurring is interesting. Beyond the difference, the possibility that different opposite things can happen at the same time. We'll be finishing quickly with this perspective. And now we are coming to Stewart Shapiro, which is probably one of the most well-known philosophers of mathematics today from the American school. Shapiro has several books about the philosophy of mathematics. One of his most famous ones is Thinking About Mathematics. And we will see what is the content of the book. Compare the content of Shapiro's book with the content of Russell's Principles of Mathematics, 1 century later. One is supposed that knowledge advances. Not true. Not true. Example, you can see here the contents of the book, of Shapiro books. He is, of course, an extremely well-respected scholar, very good philosopher of the logic, but philosopher of mathematics. Let's look a little at what is at the contents. The contents of the book are the basic ideas of truth, the deductive constructions using theorems, theories, Plato, the importance of Plato, the importance of the basic dualities between the more abstract and more concrete approaches to the philosophy of mathematics. Then the big three, the famous big three, whole chapters on the famous big three, logicism, formalism and intuitionism. That's an invention. That's an invention that has been repeated and repeated and repeated again by philosophers of mathematics, by historians of the philosophy of mathematics. It never really existed. And Russell was not a logicist. And Russell was a very open, extremely open mind. Hilbert was not a formalist. He was an extremely open-minded, in which he had beautiful texts about intuition in geometry. You cannot say that Brouwer was an intuitionistic person in the sense of the intuitionistic logic. He several times said intuitionistic logic is a kind of a strange construction. Mathematics is well, intuitionistic mathematics is well beyond intuitionistic logic. All the great minds never can be classified so easily, and the isms are an absolute aberration. Logicism, formalism, and intuitionism, three of the biggest misconceptions in the philosophy of mathematics ever. And in the contemporary scene, you introduce at least Gödel. Well, okay, Gödel exists, that's important, but that's it. In the contemporary scene, you cannot see any one of the important logicians of the contemporary scene. You cannot say that the contemporary scene is reduced to Gödel. You should say there is part of that, but what about Dasky? Dasky, much more important than Gödel for the construction of model theory. What about Lógica? What about Da Costa? What about Shellac? What about Silver? No one of the important logicians is there. So, strange. Contemporary scene seems to be very, very badly understood. And then this is, for me, like the culmination of the aberration. The Oxford Handbook of Philosophy of Mathematics and Logic. The name is strong, Oxford. Handbook, Oxford. Very important things. Philosophy of Mathematics. Well, let's see the contents. Wow, the contents is really amazing. You will see here the contents. Wittgenstein on the philosophy of logic and mathematics. He never said anything about mathematics. The logicism of Frege, Dedekind, and Russell. Mathematics doesn't appear. Logicism, formalism, intuitionism. Why? Naturally, nominally, that, etc., etc. These are all very clever, extremely clever, because these are people which are extremely intelligent, but completely invented, which has nothing, absolutely nothing to do with mathematics. It has to do a little with logic, but with very special logics. The modal logic, the classical logic, perhaps part of the intuitionistic logic, but certainly not, will never appear here. The paraconsistent logic, the logic of shifts will never appear. The model theory, the most important construction of logic in the 20th century, never appears. And you talk about philosophy of logic. To me, that's really amazing. You cannot talk about the philosophy of logic if you are not really talking about the plurality and the diversity of logics. But worse, you cannot talk about the philosophy of mathematics if mathematics never appear. Never. There is no mention of Galois, no mention of Riemann, no mention of Poincaré, no mention of Grothendieck. Nothing appears there. It's really, for me, shameful. Shameful. I was so ashamed of this book that I had to write mine.
Excellent.
This is the reason why this book exists. Because my anger with the Oxford Handbook was incredible. No? That's a small thing, but what is important is coming back a little. Let's come back a little, and I will be finishing with that, to our definitions of mathematics that we were producing last time. These are some of the definitions of mathematics, and we can remember also the beautiful definition by Russell, wonderful definition by Russell. But the most basic one, mathematics is the study of the varieties of a space and number. The most basic one. If you want to understand the space, there is no way to understand the space if you don't understand geometry and topology, at least. There is no way to understand number if you don't understand algebra and number theory. At least. It's the very basic thing. So if you are talking about Oxford book on the philosophy of mathematics, you should talk about at least a little topology, a little geometry, a little algebra, a little number theory, but it never appears. It's horrible. It's completely horrible. The varieties of space and number are the basic things that the mathematics studies. And the going back and forth between space and number has produced some of the basic constructions of modern mathematical thought. If you go from the space to number, is the great invention of the algebraic topology of Poincaré. You would try to understand the space, the topology of the space, thanks to groups, thanks to algebras, which are simpler than the topologies at the beginning, and an understanding of the groups, the homology and homotopy groups, will show you an understanding of the space, at least. So you need at least to talk a little, not so much, but a little about algebraic topology. And also, if you are interested in introducing geometry, you have to talk at least a little about algebraic geometry. A little. Riemann-Roch exists 150 years ago. It's impossible that in 2000, a handbook on the philosophy of mathematics never mentions algebraic geometry, never mentions algebraic topology, and the back and forth. If you want to now understand number through space, then you have to introduce topological forms on algebra. That's the invention of Grothendieck. Instead of the algebraic topology of Poincaré, Grothendieck inverts the thing and he introduces topological algebra. We'll talk about that perhaps tomorrow. These are the basic bridges, the basic connections between the polarities. How can you talk about mathematics if there are no polarities, there are no bridges, there is no knowledge? There is no knowledge of mathematics in the Oxford Handbook of the Philosophy of Mathematics. That's something completely unacceptable. It's unacceptable. And that's so just a small thing in my lot of possible definitions or different perspectives. So last slide, which resumes all this. Yeah. In this map of what we would call the Anglo-Saxon analytical philosophy of mathematics, in which we had a great master at the beginning of the 20th century, and then we have very, very, very bad persons at the beginning of 21st century, mathematics has completely disappeared. These things will never appear. Modern mathematics, number theory, abstract algebra, topology, differential equations, complex variables. The complex variables which were fundamental for Russell. The functional analysis which was fundamental for Shaw. Never appears. Impossible. I am really foolish. So there is a profound, I think, profound epistemological mistake in the reduction of the understanding of mathematics just to numbers, sets, and logics. Mathematics is much more complex than that. So I will just finish showing you these books in which I will present a copy to the play, to the library of the play. They will be there. My book on Grothendieck, which is a pretty heavy thing that you can throw to your adversary. It's a good weapon. And here are my books on the philosophy of mathematics. The first one, the present one on the shift models for mathematical thought that I will be talking in the fifth part, and a strange thing which my colleagues have written some articles about me. Things happen sometimes. It's a very strange thing, but that happens. Thanks.
Thank you very much for this beautiful lesson. We have 5 minutes for some questions.
Hey, good evening. I have a little question about the frame of the response that you can give to what is mathematics. A question, central question of your diagram. It appears to me that I have a commitment of division by rational and to discovery context and justification context in the results. That it develops in the end. Of course, there are three main options in philosophy of mathematics. What do you think about this frame, administrative response to that question?
No, I think it's a very interesting frame in which I will agree a lot, and which is framed also in Grothendieck's mind with the idea of invention against discovery, in which both of them are important. So the invention is the construction of the languages which will show and explain and make clear the discovery, which is very dark and very vague. The discovery is much more understood using with kinds of logic of vagueness or logic of contradictions. Instead, the frame of producing the proof is more understood with the usual classical logics or infusionistic logic, etc. So there is this heuristics, which I agree, and this duality seems to be fundamental for the mathematician. Both of the things, discovering in a non-so-clear way, and then presenting his discoveries in a much more clear way. But both of them are really important. Thanks.
Let's try you. Thanks for the talk about. Actually, I didn't know that Bertrand Russell is not a logic, right? Bertrand Russell is not a logic review, and that's I didn't know that. I have two questions about the one is about everyday Brouwer. I know that Brouwer claims that mathematics is different from logic and the situation of our mind.
Yeah.
So maybe he was not an intuitionistic logician, but intuitionistic mathematician. Right?
Yes.
Yeah. So I want to clarify those things.
Yes.
And the other,
Please.
the other question is how, according to your demarcation about mathematics, how about the mother theory and second order is in the mathematics or business mind? Because mother theory mostly deals with some kind of structure, but its subject matter is first order logic. That is my thoughts.
Okay.
Yeah.
Thank you a lot for the clarification, and in fact, extremely important one. Brouwer, of course, the founder and inventor of intuitionism, because there is an intuition of the continuum in our mind. So he has an intuition of the continuum, and that intuition of the continuum is very much framed by his studies in topology. You know that before he invented all the line of intuitionistic mathematics, he was the greatest topologist of his time, classical topologist of the time. So he had a very profound and good understanding of the continuum. And then he tried to deal with the constructive continuum. And in that construction of the continuum, he was always very fierce that we don't need logic. And the construction of intuitionistic logic is something that happens afterwards with Hating and his followers. To separate both of them. Brouwer, the topologist, the geometer, the intuitionist mathematician, and Hating, the intuitionistic logician, which opens a fantastic way of work, in which Gödel will be very important afterward. We will mention that in due moment. And the second question was about?
Yes, about how modern theory.
Model theory. Yeah, model theory is certainly a part of mathematics. It's certainly a part of mathematics, and that's, I think, the main and best example in which logic is inside mathematics. Model theory is looking at the connections between different structures. Those connections are usually done in first order classical logic, but it doesn't have to be done just in first order classical logic. It can be done either in intuitionistic logic, but also in higher order logics, and something which I call today the abstract elementary classes of Shelah, which is a wide generalization of the model theory of first order logic. So model theory lies, and this is probably the best example of a part of logic which is inside mathematics and which cannot be taught without mathematics. Mathematics is really fundamental for them, because there you have all the fundamental structures. There you have topology, there you have algebra, there you have order. All the fundamental structures are there. That is not so in the logical calculus. The logical calculus tries to usually don't go to that level of sophistication.
Professor, we have to finish, but
Yeah.
After we could discuss, I don't know if I agree with you. I think that model theory is a good example concerning the interrelation between mathematics and logic, not that logic is inside mathematics.
Okay.
Okay?
We will have to discuss
Yes,
that, but
yes.
I do think that it's part of it.
Yes, it's not so easy. It's
If we were describing the attitude of the contemporary American philosophers of mathematics, I thought was I don't know much about what mathematics, much more specialist in metaphysics, but the kind of attitude you describe is very similar to the attitude of this tradition regarding metaphysics, which is it seems like they act as if there are others didn't exist. The others of that tradition, they didn't exist. They don't even want to talk about them, which is a kind of subtle, violent attitude.
Yeah.
I'm not going to entitle myself to talk with you. And my question is, do you think there is a political basis over that grounds this attitude? Or do you think it's just naive, lack of curiosity, something like that?
That's a very hard question. I hadn't thought about that. It is probably that the political mind influences each of us a lot more than we think. And it is possible that just the American understanding of the world, that the world is understood through America, through English. We are talking English. I don't know why we are talking English. We were talking about with Carnielli that I should give my talk in Spanish, and almost all of you will understand. If not, you will make the effort. Joao will give his lecture in Portuguese. We will, almost all of us, understand. We should try to do these things. So there is a kind of clear. I don't want to use explicitly the word imperialistic, but something of a canon. There is a a canon of strong impositions of language, strong impositions of dogmas. For me, this is the exact good example, very, very good example to finish our talk, in which this thing becomes a dogma. The Oxford Handbook of Philosophy of Mathematics and Logic does not serious, but it's Oxford, it's English, and people take it seriously. But it is ridicule. It's completely ridicule. You cannot say that that's philosophy of mathematics. It's extremely away. Extremely.
Sorry, we don't have more time.
Okay.
Thank you very much.